Sobi, can you see my screen? Okay. Okay. So we start by 6:5. Means, can you repeat what you are saying? You can find out on the NPTEL portal. The link is shared on that. Which part? Okay, okay, path. Huh. So the file path is just when you go to the course in the uh, respective weeks, there are links for respective recordings. Or in the notification page also, you can see the reminders for this doubt solving session and the uh, this recordings. Means Okay, so you can ask in the discussion forum also if you have any doubt. In discussion forum, or I will share my screen and show you how to. Link. So this is the course page, right? So here, problem solving session, problem solving recordings. You can see. Yes. So when you click here, this Excel sheet is provided, so you can see the recordings for all weeks from week 1. Can you see my screen? Uh, so in this page, click on the Q&A option. So you will go to the discussion forum. So here you can ask. The professor and I both can see the queries here. Discussion forum for this course. So you can start a new conversation here. So when you it will, so we will get the email also when you ask any query. Yeah, means I take the doubt solving session of the previous week. So if you have any doubt regarding the previous week lectures, so you can ask in today's session, or if you have, so when you go through the next week this week lecture, so you can ask in the next doubt solving session. Every Tuesday it happens, and in the discussion forum also. Anytime, your discussion forum, you can put query in anytime. Okay. Okay. Have you go through the week 5 lectures? That- Okay. Okay. So, and what about week 4 means? Are you following the all week lectures? Oh, okay, okay. So I will discuss these problems for the today the problems is regarding the week 5 lecture. So I will explain the concept little bit here also. So in the week 4 lecture we studied about the yield criteria and the tensile testing concepts. All means how we calculate the ductility, tensile strength, uh, yield strength, and the true stress strain behavior. So in this class we studied about the uh, strain hardening behavior of the material. So you see in the uniaxial tensile test means the curve looks like the stress strain curve looks like this sigma epsilon, and this curve is for the, so up to this point this is the yield strength, and this point is the tensile strength. So between these 2 points, the behavior of the material is different as means the behavior before the yield strength. So this is the plastic region and this is elastic. So in the plastic region, the we follow that strain hardening behavior means as the material deform, it get strain hardened due to formation of dislocations. So the stress required to deform it more increases with the deformation. So this behavior we can uh, show the power as a power law. So K epsilon raised to power n, and so K is the strain hardening coefficient, strengthening coefficient, and sorry, sigma and epsilon is the stress and strain, and N is the strain hardening exponent. So one more criteria comes here, like if so this is at a strain rate, and what if we change the strain rate during testing, or we test the same material with different strain rate values. So that behavior is written as sigma equals to C. This is the strain rate E dot raised to power M. So here C is some strengthening coefficient, and M here is the strain rate sensitivity, means how the material behavior is changing with changing this with change in the strain rate. So M here is the, so I will write N is the strain, yeah. So N here is the strain hardening exponent, and M here is the strain rate sensitivity. Means either the material will get softened or hardened. So that depends on this M value. So okay, so this strain rate sensitivity, we we do test at multiple values of strain rates. So that's why that's how we can uh, show means see the behavior of the material at different strain rates. So what is the purpose of changing strain rates uh, in in the practical point of view? Can you ask, means think like what is the purpose of changing strain rate? Mridula and Souvik, can you answer? Like what we why we change the strain rates? Yeah, that is correct. And one more thing, in the practical scenarios in industries, when we make any products from these metals, so in that perspective, means in the lab we do uniaxial tensile test. So that is the quasi-static condition. But in the industry, we cannot fix the quasi-static conditions every time. We generally do forming operations like rolling, forging, and deburring at higher strain rates than the causostatic. So, in that condition, we require the material behavior so that we can ensure the quality of the products. So, means how it will deform or not deform. So, in at industry level, we generally use the highest strain rates on also only. So, the both quasi-static and dynamic behavior of the material, we should know about that. Sorry, I didn't get. Yeah, hmm. You can ask which doubt you have. Yes, yes, Yeah. Yes, so we can do operations to homogenize the microstructure. So during the forming operations, we can do, means there are two types of forming, cold forming and hot forming. So in both the microstructure will vary. So by doing the intermediate processing, we can means optimize the microstructure of the that material we are what we are using. Yeah, homogenization and so in the steel we can use many types of heat treatments we use like normalizing, quenching. So by optimizing all these processes we can maintain the microstructure. Okay, just 1 second. Yeah, sorry. Yeah, so we'll solve the problem now. So the strain M here is the strain rate sensitivity. So so in the exam, this problem, we have asked that the strain rate dependence of a zinc alloy can be represented by equation 6.1. So the equation 6.1 is this only: sigma equals to C uh, epsilon dot raised to power m. So where with m equals to 0.07. So what is the ratio of the flow stress at strain 0.1 for a strain rate of 10 raised to power 3 per second to that same strain for a strain rate of 10 raised to power minus 3 per second. And we have to repeat for a low carbon steel with the the m value 0.01. So So how can we solve this question? We have given a strain rate and m value for two strain rates. So we have to uh, find the ratio of flow stresses at this. So first if we write this equation, so for sigma, for the initial condition sigma 1, we can write C equals to epsilon dot 1 raised to power m, and sigma 2 is to C E dot raised to power m. So if when we divide these two equations, so the sigma 2 by sigma 1 will be C will so cancel out 2, and we can write E2 by E E dot 1 raised to power m. So E2 is the 10 raised to power minus 3, and divided 10 raised to power 3 raised to power m. So for a strain rate of 10 raised to power minus 3, yes, this is sigma 1 and this is sigma 2. So here this is the first condition, this is second. So we'll take this 10 raised to power 3 as the second, and this is minus 3. So then when we it will come in the sorry. So this will be 10 raised to power 6 raised to power m. So here m value is 0.07. So this will be equal to 2.63. So this is the ratio of the flow stress. And if we want to calculate this for steel, so it will be 10 raised to power 6. M is 0.01. So that will be 1.15. So one more thing, the value of M also show material behavior. Means if a material have M value less as compared to the other material. So here we have M 0.07 for zinc and M 0.01 for the low carbon steel. So the strain rate sensitivity of steel is less as compared to the zinc. So means the zinc will uh, uh, response. So the response of the changing strain rate is much more higher in the zinc alloy as compared to the low carbon steel. So we'll go to the next problem. So the in this question, for an aluminium alloy under constant load, the creep rate increased by a factor of 2 when the temperature was increased from 71 degrees Celsius to 77 degrees Celsius. So find the activation energy. So here a creep is given. So the this behavior of the material also depends on the strain rate and temperature. So the for the uh, creep behavior at two temperature or creep rate, we can here write as strain rate also. So for this the temperature dependence of the material is represented by a constant that is known as the Zener-Holman equation. So so Z is the sigma, no, not sigma. App means strain rate ln of exponential of q by rt. So the this Zener-Holman constant will be equal for a material at some for some variables. So here q is the activation energy and T is the temperature. T is temperature in Kelvin. So this constant will be equal at both temperatures. So we can write the equation E1 E dot 1 exponential of uh, Q by RT1 equals to E dot 2 exponential of Q by RT2. So when we take log from both sides, so this will be ln E dot 1 plus Q by RT1 equals to ln E dot 2 plus Q by RT2. So from this we can further write Q by R 1 by T1 minus 1 by T2 equals to ln E2 minus ln epsilon 1. So from here we can write activation energy as ln E2 by E1 divided uh, R 1 by T1 minus 1 by T2. So when we put, so creep rate increased by a factor of 2. So means E2 is 10 raised to power 2 and E1 is 1 per second. Factor by increases by a factor of 2. So it is 10 raised to power 2 and 1. So, and the temperature is 71 plus 273 and 77 plus 273. So when we put this ln here, so this will be ln 100 by the R value is the gas constant, so it is 8.314, and here it is 344 minus 1 by 350. So by solving this, we can get the activation energy as 116 kilojoule. So the means the unit for this gas constant is joule per mole. So the unit for this activation energy will be the same. And so we'll solve the next problem. So we have asked that during a tension test, the rate of straining was suddenly doubled. This caused the load force to rise by 1.2%, assuming that the strain rate dependence can be described by this. So what is the value of M? So we have to uh, find the value of M. So we have given the strain rate and stress ratio value. So we can write as sigma 2 by sigma 1 uh, E dot 2 E dot 1 raised to power M. So this will be here sigma to rise by 1.2%. So 1.2% will be 1.2. So this we will add. So this is 1.012 of sigma 1 divided sigma 1, and this is the strain rate got double, so 2 by 1 raised to power m. So the sigma 1 will get cancelled out, and ln of 1.012 equals to ln of 2 into m. So we can get the value ln like this. So this will give the 0.017 strain rate sensitivity value. Okay, so in the next question, it is based on the same. So the two tension tests were made on the same alloy, but at different strain rates. Both curves were fitted to a power law straining hardening expression of the form sigma equals to k epsilon raised to power n. So this is the power law uh, for the strain hardening. So yeah, one more thing I have to say. So this is the strain hardening behavior, and this is the strain rate hardening. Okay, so to a power law. So the results are summarized in this table. Assuming that the flow stress at a constant strain can be approximated by this equation, determine the value of m. So yeah, we have given strain rates, the constant of this. So we have to find the sigma value for both test A and B, and by putting in the second equation, we can find the m value. So let's continue. Like sigma equals to k is the 400, sigma 1 is 402 for a same strain. So if we consider a same strain, epsilon, and here n value, or we can consider the strain of zero point 0.1. So here n 0.1 and value is 0.22. So the sigma 1 we are, mhm. So we have got 242.22 amperes, and for the test B, sigma 2 is 412.1, and the strain hardening is 0.22. So this will give 248.25 ampere. So we know that the sigma 1 and sigma 2 value, and strain rate also we know. So we have to find the value of m. So m can be written as ln of sigma 2 by sigma 1 and ln of E2 by E1. So this will be ln of E2 is 10 raised to power minus 1, and this is minus 3. So this is ln of 1.025 divided ln, this is ln 50. So this will give ln of, yes, so this will give the strain rate sensitivity 0.0063. So these type of questions will come in the assignment and the exam also. So we'll go to the some previous assignment questions, and this assignment question also we will solve. So this first question is easy. Can you answer? So we have asked that which of the following are true regarding plastic instability and necking during a uniaxial tensile testing. So plastic instability you studied in the week 4 lectures. So can you answer? Which option will be correct? Tensile behavior of a material means tensile testing. A professor uh, taught in the week 3 and week 4 lectures. Okay, then I will explain it. So, the plastic instability and necking during a unique shell tensile test, we can show like this. So, this is the up to UTS, and the this is the fracture of the material. So, this point he is known as the plastic instability point. So, up to this point, the material deformation is uniform. Means if we deform this material, so it will elongate with a uniform cross section area. But after this point, UTS, the deformation gets localized at some region, and the uh, necking of the material starts. So, the deformation gets localized at some region, and the further deformation will happen on this region by because uh, the local stress at this point is higher, so that only this area will get deformed and lead to fracture of the material. So can you answer the this question now? Means which option is correct? The material load carrying capacity increases once necking begins, or necking leads to a uniform reduction in the specimen cross-sectional area, or after the onset of necking, engineering stress decreases as engineering strain increases, or plastic instability is associated with a localized or unstable deformation zone. So which option is correct? Are you here? Are you here, Rohit? Okay, so I give the answer. So in this, the C and D option is correct. After the onset of necking, the engineering stress decreases as engine strain increases, and the plastic instability is associated with localized unstable deformation zone. So C and D is correct. In the next question, for a material exhibiting necking under uniaxial tension, the true stress at the point of plastic instability is given by the expression. So which uh, uh, option is correct? So in plastic instability, we write d sigma by d epsilon equals to sigma. So this a term comes after the derivation from sigma equals to f a. Okay, okay. Yeah, so the instability, we got this term by differentiation by of this term, this sigma equals to fa. So in the the plastic instability equation is given by this formula. D sigma by d epsilon equals to uh, sigma, means this condition is, means this is the sigma epsilon, and the this d sigma by d epsilon curve means this is the strain hardening rate. So when we draw a curve of the d sigma by d epsilon versus sigma, yeah, so strain or d sigma by d epsilon. So when we draw a curve for this, so generally we get this behavior. So at this, or generally, so this curve is sigma versus epsilon, and this curve is d sigma by d epsilon versus epsilon. So at this point, this d sigma by d epsilon is equals to sigma value. So this point is the plastic instability point, and also we know this point as the considers criteria. Yes. In the upper segment, no, it for a material means is it is the definite nature, means the strain hardening rate will be equal to the strain value at this plastic instability. So this plastic instability point is generally the UTS point. So at the UTS, means it is fixed. At UTS, this strain hardening rate will be equal to the value of the stress at that strain. Yes, at this point. So means the here also na. So uh we got this no true strain means the uniaxial tensile behavior like this. So after UTS, only the curve decreases, and up to UTS the material deform uniformly, and after UTS it starts, means the deformation localized at some point. So that localized deformation happen after the UTS. So only at UTS the this behavior will follow. Means the strain hardening rate will be equal to stress value at UTS. So from this equation, the plastic instability is given by this equation, sigma equals to d sigma by d epsilon. So next question we have asked, like calculate the percentage increase in flow stress when the strain rate increases by two orders of magnitude. Uh, it means E2 dot by E1 dot is 100 at temperatures of 440 and 25 degrees Celsius. So use the data for commercially pure aluminum the constant true strain of this 0.25 and assume that the flow stress is approximated by this equation. Yeah, so here we have given this. This is the C and this is M. So we have given C value of C and M at two temperatures, and just we have to we have also given the strain rate ratio. So just we have to find that by what percentage the flow stress increased. So if we calculate it, like first for 25 degrees Celsius, sigma 2 by sigma 1 will be, C will cancel out, so we can write E2 E dot epsilon by 1 raised to power m. So it is 100 raised to power this m value 0.066. So this will be equal to 1.35. So if we minus and decrease, so it will be 0.35, and if we multiply it by 100, so this will be 35%. Similarly, if we uh, calculate for the 440 degrees Celsius, so this will be 100 raised to power this m value 0.211. So this will be 2.64, and if we decrease, so this will be 1.64 multiplied by 100, so the change will be 164%. So the option, so from the option, the D option is correct for this question. So we have to find the percentage increase in flow stress. Okay, so go to next question. So what are the necessary conditions for a material to display superplasticity? So you know about the superplastic behavior. Okay. So the superplasticity is the state of a material when we apply a small amount of stress and it deform, means it, very large extent, means for a small amount of applied stress, the deformation is very high. Uh, so the deformation can be achieved up to 2000%, means uh, for a small, for a, so the 2000% elongation is very high. uh, so this condition of material uh, occur for some specific type of materials, means the if it shows the high strain rate sensitivity, means we discussed just uh, means in the previous questions, like if m value is less, so the material sensitivity towards the changing strain rate is less. But so less sensitivity means if we increase the strain rate, so it means the impact of that changing strain rate is very less. But if M is very high, so the sensitivity will be also high. So when the sensitivity of the material will be very high, so with a change in values of strain rate with very small amount, the material will show a very high change in the deformation. So the first condition is that strain rate sensitivity should be very high, and this generally occurs in the extremely fine grained microstructure materials. Fine grain, and the temperature at which we are applying the stress should be greater than zero point 0.5 Tm. Tm is the melting temperature. So zero point 0.5 Tm is also the homologous temperature. Derivation you can find in books, but or I will explain it in the next class. But for this superplasticity, the strain means deformation should happen at this temperature only. So if we are providing this zero point 0.4 zero point 0.4 of the melting temperature, and the material having very fine grained microstructure and very high strain rate sensitivity, so that material will show the superplasticity behavior. Yeah, equixed also. Fine equixed grain size. So from this, and also means we have a very high strain rate sensitivity. So we means लाइक हमको ज्यादा स्ट्रेन रेट बढ़ानी नहीं पड़ेगी, मतलब एट वेरी लो स्ट्रेन रेट वैल्यूज we can achieve the high strain rate sensitivity because the M value is very high. So for the superplasticity, the we require both low strain rates, high temperature, extremely fine fixed microstructure, and high strain rate sensitivity. So the all options are correct, uh, the for the necessary condition of this superplasticity. Okay, so can we move forward to next question? Okay. So next question is, if a strain hardening exponent n is large, so so this question is related to the week 5 lectures only. So in that lecture, the professor told that if we have and well, so here we have discussed that what is the behavior of M changing. So the one more behavior is related to the strain hardening exponent N. So if we have N very less, so in this condition, the initial strain hardening uh, rate is very high, but uh, saturates at early deformation. But if N is very high, So in this condition, the initial this strain hardening rate is slow, and it it continues to deform material to high strains or deformation. Means for high value of n, means if strain hardening exponent value is very high, so the initial strain hardening rate is slow, but it continues to very high deformation level. But for less value of strain hardening exponent, the initial rate is very high, but it saturates for a very less amount of deformation. Like we can see this behavior from the stress strain curve. For n value less, so the curve is very steep, and it will stop here, and the material will fracture. And for, so this is for n uh, value, low n value, and for high n value, uh, this behavior will show. So it will uh, deform the material to a higher strain values. So this is for large n value. So if you ask that, if you have asked in any question, these two curves, so which will show the n value large, and which is the shows the n value of low n value. So uh, this curve is for the low n, and this is for the large n values. So can you answer this question now? So the first option is correct from this fifth question. Means if n value is large, work hardening rate is initially less rapid but continues to high strains. Okay, so we'll go to next question. So we have asked that a mild steel specimen is subjected to a tensile test at different strain rates. The following data is given for this tensile test. Means stress value at the two strain rates. So determine the strain rate sensitivity of the material and the flow stress at a strain rate of 10 raised to power minus 1. So first we have to find the value of M, then the flow stress at this strain rate. So the M is written as ln of strain rate 2 by E1, no, sigma 2 by sigma 1, ln of E, E dot 2, E2, E1 dot. So this will be the, this is second, 330 by 300, and ln of 10 raised to power minus 2 by 10 raised to power minus 3. So this will be ln of 1.1 by the ln of 10. So this will give M value 0.0414. And if we want to calculate the flow stress, so the flow stress will be, so first we have to calculate the value of C also. So when we put this will be 330 divided 10 raised to power minus 2 raised to power 0.414, So this will be 399.3 ampere. So when we derive for this, 10 raised to power minus 1 raised to power 0.0414. So this will give 363 ampere. So the second option have the correct value. So go to next question. So uh, seventh question asks that during the hot deformation testing of a material, the temperature was raised from 100 to 150 degrees Celsius. In order to maintain the same flow stress for deformation, the strain rate had to be increased by a factor of 100. The activation energy for the mass transfer mechanism will be, yeah, so here we have to calculate the activation energy. So the activation energy we derive the formula in the previous problems. So this is ln E2 dot by E1 dot multiplied by R and 1 by T1 minus 1 by T2. So here R is given 8.314, ln is 100 by 1 divided 1 by 100 plus 273, that will be 373 minus 1 by 150 plus 273 will be 423. So this will give 121 kilojoule. Yeah, so in this question, this first option is given wrong. So the but correct option, correct answer for this is the 121 kilojoule only. So we'll go to next. Which of the following is true about the Burgers vector? So Burgers vector is related to the dislocation. So maybe you haven't go through that lecture. So the Burgers vector of a dislocation means this is the, so this is means this extra half plane of, so means if this is a atomic arrangement in a crystal and more planes are complete, but the middle plane is incomplete, only it is half. So this half plane is called as the dislocation. So for this dislocation means if we want to uh, find the Berger vector for this, so we have to do some calculation. Like first we have to, uh, so we do some uh, circuit or path. So first we will start from this point. So we have to go 1, 2, 3, then 1, 2, 3, then from this point 1, 2 and 3, and at the upside 1, 2, 3. But this circuit is not complete when we come at from start to finish. So the we have to find the vector direction and the magnitude of that vector to complete this circuit. So the vector which complete this circuit is having the distance of this atomic distance, then only this will, so this vector is generally known as the Burgers vector of dislocation. And so in the metals, this distance is generally occur at the highest atomic density planes. So at the highest atomic density planes only we have to uh, travel from one atom to another atom. So it is the shortest distance lattice translation vector, shortest lattice translation vector, and the dislocation moment is called as the slip. So this slip, it is also known as the slip vector. So the from the options, the first option is correct. It is same as slip vector. It is the shortest latest translation vector, and so Berger vector is not the direction; it is the vector. So this fourth option, vector that closes the Berger circuit. So this D option is also correct. So A, B, and D is correct. So next question will go to, so yeah, for the magnitude of Burgess vector for face-centered cubic crystal with lattice parameter A is, yeah. So just now I told that for metals it happens at highest atomic density planes. So FCC is the face-centered cubic crystal. We have uh, two types of planes. So atoms are at corners, and it face centered also. So the highest atomic density will occur at this plane and in this direction. So the highest atomic density will be at each face. So if we want, so if the this unit cell spacing is A, so we have to find. So this is only also A, because this is cubic. So we can find this distance as x equals to square root of a square plus a square. So this will give root 2a. But the distance we have to travel only half. So the magnitude of Berger vector will be x by 2, will be root 2 by a by 2. So this will give a by root 2. So the correct option for this is C, a by root 2. Similarly, we can find the Berger vector for the BCC and simple cubic also. So next question we have asked, like this is figure shown. So this figure shows both screw and edge type of dislocation. Means this is the screw dislocation from this point, and this from this point we are seeing extra half plane. So this is the edge dislocation from this face. So we asked that mark the correct option from by seeing this figure. So which first will um, so, here we have given that A is screw dislocation and B is edge dislocation. Yeah, so the first option is only correct. A is edge dislocation, B is screw dislocation. This is wrong. Both A and B are edge dislocation. This is wrong, and this is also wrong. So A is the screw uh, dislocation and B is edge dislocation. Okay, so we'll discuss some more questions. So these questions are from the recent assignment. So, uh, so we have asked that flow stress of a material is given by this sigma equals to k epsilon raised to power n, which or the following value of n will give the highest uniform elongation in the material during uniaxial tensile testing. Yeah, so in this equation also, when you uh, study in the professor videos, so in that one term comes like when we differentiate this equation with respect to n, so d sigma by d epsilon will give k epsilon power n minus 1 into n. So we can write it as n by epsilon, and this will be k epsilon raised to power n. So this is the same term as here. So, and we know that the d sigma by d epsilon at UTS at and uh, at maximum load, d sigma by d epsilon equals to sigma. So the sigma will can, so this is k by epsilon, this is sigma, so this will cancel, sorry, n by epsilon. So here n equals to epsilon means the strain value. So they have a linear relationship and the direct correlation. So if we have higher n value, so the strain will also be higher. So which option will be correct means we have asked that which of the following value of n will give the highest uniform elongation, and E is the uniform elongation. Sorry, epsilon. So which option is correct? You can write in the chat box also. So the correct option for this is the D. Point 0.4 will give the highest uniform elongation. Okay, so the next question says that flow stress is proportional to strain rate raised to power m, where m is the strain rate sensitivity. So if m equals to 0, what will be the behavior of the material? So if m is 0, the material generally rate insensitive, means if we increase the strain rate to any level, that will not show any strain rate sensitivity. So the C option is correct for this. Next, a material with a strain rate sensitivity of 0.05 is tested at two strain rates. If the ratio of the strain rates is 10, then the ratio of the flow stress of the material under these two conditions will be, yes, so just we have to find sigma 2 by sigma 1 will be epsilon 2 dot by epsilon 1 dot raised to power m. So we have given the ratio 10. raised to power 0.05. So this is equal to 1.122. So the first option is correct. Uh, Next question we have asked that necessary conditions for a material to exhibit superplasticity. So this is the same question we have discussed. So first, which option is correct? We have to see. Like very high strain rate. No, we require at low strain rates only we can achieve the superplasticity and high temperature. So this option is correct. Coarse grain microstructure, no. We require fine aqueous microstructure, so this is wrong. And high strain rate sensitivity. So the B and D option is correct. Next question. During the hot deformation of a material, the temperature was increased from 100 to 150 degrees Celsius to maintain the same flow stress of deformation. Strain rate had to be increased by a factor of 100. The activation energy for the mass transfer mechanism will be. So this is the same question we solved. So the correct option Q activation energy is 121 kilojoule per mole. So the first option is correct. Next question we have asked that a perfect crystal without dislocations is subjected to shear deformation. Would it be softer, require extremely high stress to deform, be superplastic, or show zero strength? So, from the lecture videos, we studied that the perfect crystal require very high strength. Means the dislocation soften the material so that it can deform at low with a low application of the stress. So, if we have very perfect crystal without dislocation, so it is very hard to deform it. So the second option is correct, require extremely high stress to deform. Next question is which of these dislocations have dislocation line vector perpendicular to Berger vector? So we have two types of dislocation like edge and screw. So in the edge dislocation, the line Berger vector B is generally perpendicular to line vector. Line vector is the slip line, and for the screw, Berger vector is parallel to line vector. So for pure edge dislocation, the dislocation line vector is perpendicular to Berger vector. So the first option is correct. Next question: which of the following statements are correct for a screw dislocation? So in a screw dislocation, atoms are arranged helically. Yes, first option is correct. Means the if we see the arrangement of atoms in a screw dislocation, so that we can every time we go through a path, so we will uh, step up on top by one atomic plane. So atoms are arranged helically. So in that, right hand and the left hand screws are physically same. No, this is wrong. The both will be equal. No, both will be different screw dislocation. And the Berger vector is parallel to dislocation line, so this is correct. And the last option is also wrong. So A and C is correct for this question. The ninth question we asked that a Berger circuit is drawn around a defect inside a crystal lattice. What will be observed if a dislocation is present? So if a dislocation is present, the Berger circuit will not close, and the vector which we need to close it is known as the Berger vector. So the second option is correct. It does not close. The last question is the magnitude of Berger's vector for simple cubic crystal with the lattice parameter is. So uh, first we have to draw the simple cubic lattice unit cell. So the atoms are only at corners. So the atomic density is equal for all planes. So we have to find the distance from one atom to another. So this is if unit cell parameter A. So the dislocation Berger vector will also be equal to this A. So the first option is correct for the simple cubic. So one more thing, if we want to derive the this Berger vector for FCC, we have derived that is A by root 2 for FCC. For simple cubic, it is A, and for BCC, what will be? So for BCC, if we draw, so atoms are at corners, and for body center, one atom is there. So the shorter distance will be this body diagonal, half of the body diagonal. So if the unit cell length is A, we have to find this. So first we will calculate this. Yeah, so the body diagonal generally for any material is root 3A. I calculate. So means we have to first find this. So this is the root 2A. This is A. So this will be the body diagonal will be square root of root 2A square plus A square. So that will be root 3A, and the Berger vector will be half of this. So Berger vector B will be root 3A by 2. So this for this will be root 3 by 2A. So these are the Berger vector for FCC, simple cubic, and BCC. So do you have any doubt regarding today's session? If not, we can end the session. So you can ask the doubts in the next class also if you haven't gone through the lecture videos. Okay, thank you.